Today let's discuss the Pyqs of real analysis asked in 2025 examination of UPSC CSE. There were only 4 questions asked on this topic, so let's see them one by one. So question 1 is, examine whether the given series, that is summation n equals to 1 to infinity minus 1 raise n minus 1 divided by n is absolutely or conditionally convergent. So we are supposed to check whether this is absolutely convergent or it is conditionally convergent. So let's see how we can do that. First of all, if you observe that this is basically an alternating series. So we'll be using Leibniz test to check its convergence. So what does Leibniz test states is, Leibniz test states that any series of form, let's say summation minus 1 raise n bn is convergent if the given series b, if the given term bn is basically positive, it is decreasing, basically this term is decreasing for all values of n, and limit n approaches infinity bn is equals to 0. Now let's say if the given series satisfies this Leibniz test or not. So if we compare, bn will be equals to 1 by n, and you can see that for all n belonging to natural number, bn is basically greater than 0. So from here we can say that our bn is positive. Also, we know that n is always less than or equals to n plus 1 for all n belonging to natural number. So from here we can say that 1 by n plus 1 will be less than or equals to 1 by n. That is, bn plus 1 is less than or equals to bn for all n belonging to natural number. So from here we can say that bn is basically decreasing. And if I evaluate this, that is limit n approaches infinity bn, it will be equals to limit n approaches infinity 1 by n, which is equals to 0. So basically bn satisfies all the conditions that are there in the Leibniz test. So from here we can say that by Leibniz test, given series is convergent. By Leibniz test, given series is convergent. Now we'll check its absolute convergence. So if I evaluate this, minus 1 raise n minus 1 1 by n summation, it will be equals to summation 1 by n, which is basically a divergent series. A divergent series, we can say that using p test. So from here we can say that our given series is basically, given series is convergent but not absolutely convergent, So our series, that is summation n equals to 1 to infinity minus 1 raise n minus 1 times 1 by n is conditionally convergent. This basically completes our question 1, in which they have asked us whether the series is absolutely convergent or conditionally convergent. So our given series is conditionally convergent. Let's move on to discuss the next question. So the next question is, define Cauchy sequence, and it further asks us prove that every convergent sequence of real number is Cauchy sequence. So first is to define Cauchy sequence, and second is to prove that every convergent sequence of real numbers is Cauchy sequence, and it further asks us the importance of Cauchy condition. So the definition is, if Sn is a sequence it is said to be Cauchy sequence if for a given epsilon, given epsilon greater than 0, there exists m belonging to natural number and p belonging to natural number such that absolute value of Sn plus p minus Sn is less than epsilon whenever n is greater than equals to m and for all p greater than or equals to 1. And here basically my n and p and m are natural numbers only, or absolute value of Sn1 minus Sn2 is less than epsilon whenever n1 comma n2 is greater than or equals to m, and here m also belong to natural number and n1 and n2 are also natural number. Now let's prove that every convergent sequence of real numbers is Cauchy sequence. Now our claim is every convergent sequence of real numbers is Cauchy sequence. Now let Sn be a convergent sequence. Let Sn be a convergent sequence. So if Sn is convergent, so for any given epsilon greater than 0, there must exist m belonging to natural numbers such that absolute value of Sn minus L is less than epsilon by 2 for all n greater than or equals to m. And here our L is basically the limit to which Sn is converging. L is point to which the given sequence Sn is converging. Now we are supposed to show that the sequence Sn satisfies the Cauchy condition. Now if you observe that if the given sequence Sn is convergent, so this relation basically equation 1 holds for all n greater than or equals to m. So it should hold for n equals to n plus p as well. So we'll get Sn plus p minus L is also less than epsilon by 2 for all n plus p greater than or equals to m, and here p is greater than or equals to 1. Now I will claim, now our claim is to show that absolute value of Sn plus p minus Sn is less than epsilon for all n greater than or equals to m and for all p greater than or equals to 1. Now if I evaluate this, that is Sn plus p minus Sn, this term can be written as Sn plus p minus L plus L minus Sn. Now by triangles inequality, this can be written as less than or equals to Sn plus p minus L plus L minus Sn, which is same as writing absolute value of Sn plus p minus L plus Sn minus L, and this thing is less than epsilon by 2 and this thing is also less than epsilon by 2 using equation 1 and equation 2, and it holds for all n greater than or equals to m and for all p greater than or equals to 1. So from here I got that Sn plus p minus Sn is less than epsilon for all n greater than or equals to 1 and for all p greater than or equals to 1. So from here I can say that Sn is a Cauchy sequence. As it satisfies Cauchy criteria. As it satisfies Cauchy criteria, and that's what we are supposed to show, that if Sn is any convergent sequence then it satisfies the Cauchy criteria. Now there's another part of the question which says that what is the importance of Cauchy condition. So basically importance is, we have a result which states that in basically for any real sequence, like for any real sequence Sn, so a real sequence Sn is convergent if and only if it satisfies the Cauchy criteria, or if it's a Cauchy sequence, if and only if it's a Cauchy sequence. So basically it, for any real sequence, it's enough to show that it's convergent, it's enough to show that it is basically a Cauchy sequence, which at times is pretty much easier than actually showing that it is convergent. So that's the importance of Cauchy criteria or Cauchy sequence. Now let's move on to discuss the next question. So the next question is, prove that every continuous function is Riemann integrable. So we are supposed to show that every continuous function is Riemann integrable. So for that, let us assume that fx is any continuous function, on closed interval a comma b. Now we are taking closed interval a comma b because that's the necessary condition for any function to check a Riemann integrability or not. So that's why we have taken closed interval a comma b, and we know that any continuous function on closed interval a comma b is also uniformly continuous. So using this result we can conclude that fx is uniformly continuous on closed interval a comma b. Now if we use its definition, so for any given epsilon there exists delta greater than 0 such that absolute value of f x1 minus f x2 is less than epsilon divided by b minus a whenever absolute value of x1 minus x2 is less than delta. And since it is uniformly continuous, so this delta is dependent upon epsilon only, not on the point x. This delta uniformly works for all points in the interval a comma b. Now this is basically the definition of uniform continuity. Now let us assume that P be any partition of a comma b with norm of p, or you can write it as norm of p as less than delta. Now let's name this as equation 1 for convenience. Now using equation 1, which states that f of x1 minus f of x2 is less than epsilon divided by b minus a. Now since our interval, that is a comma b, is closed and bounded, so the function attains its maxima and minima within the interval. So there exists at some point within the interval at which function f attains its maxima and minima. Now let mr minus small mr be the maximum, like this, let this be the max value and this be the min value in x delta xr interval of the partition P. Then this is also less than epsilon divided by b minus a using 1. And why we are able to write this? Because the function is defined over closed and bounded interval, and on closed and bounded interval function, basically there always exists point where function attains its maxima and minima value. Now since fx1 minus fx2 is less than epsilon by 2 for all x1 minus x2 less than delta, then mr minus small capital mr minus small mr should also be less than epsilon by b minus a using the above relation, and it holds for all r equals to 1, 2 up till n if P is a partition with n subintervals. Now if I calculate UPF minus LPF, so it will be equals to summation r equals to 1 to n capital mr minus small mr times delta xr, where delta xr is basically length of rth subinterval for the partition P. Now this will be less than epsilon divided by b minus a times summation delta xr, where r varies from 1 to n, and this will be basically equals to delta xr, summation of delta xr will be basically equals to length of whole subinterval, that is b minus a. So it will be epsilon divided by b minus a times b minus a, which is equals to epsilon. So what we just got is UPF minus LPF is less than epsilon whenever norm of P, that is less than delta, and this delta is basically dependent upon epsilon only. So from here we can say that since the difference of upper lower sum and upper Riemann sum and lower Riemann sum is arbitrarily small, so we can say that using this relation we can say that the given function fx is Riemann integrable on closed interval a comma b, and that's what we were supposed to show in this question. So let's move on to discuss the next question. So the next question is, show that the volume of greatest rectangular parallelepiped that can be inscribed in the given ellipsoid is 8abc divided by 3 root 3. So let x, y, z be length, width and height of given parallelepiped. Or let's just say that 2x, 2y and 2z be the height of given parallelepiped, because that will make calculation a bit easier. So let 2x, 2y, 2z be the length, width and height of given parallelepiped. So from here volume of parallelepiped will be equals to 2x times 2y times 2z, which is equals to 8xyz. Now this question is basically based on Lagrange's multiplier method. So this is not technically a question of linear real analysis, it is basically a question of calculus, but since it's asked in paper 2, we'll discuss it here only. So if I define capital f x y z function, it will be equals to 8xyz plus lambda times the given condition, that is the equation of parallelepiped, that is x square by a square plus y square by b square plus z square by c square minus 1. Now in order to calculate its stationary point, if I find a df, that will be equals to 8yz plus 2 lambda x by a square times dx plus 8xz plus 2 lambda y times b square times dy plus 8xy plus 2 lambda z by c square times dz. Now in order to calculate its stationary point, df must be equals to 0. So from here I'll get 8yz plus 2 lambda x by a square equals to 0. 8xz plus 2 lambda y divided by b square equals to 0, and 8xy plus 2 lambda z divided by c square equals to 0. Now if let's name them as star 1, star 2 and star 3. So if I multiply x in star 1 times x, and multiply y with star 2 and z with star 3, so what I'll get is 8xyz plus 2 lambda x square by a square equals to 0, and here I'll get 8xyz plus 2 lambda y square by b square equals to 0, and here I'll get 8xyz plus 2 lambda z square by c square equals to 0. Now what I can do is, if I evaluate value of 8xyz from here, so it will be equals to minus 2 lambda x square by a square. From here it will be 8xyz will be equals to minus 2 lambda y square by b square, and here it will be 8xyz will be equals to minus 2 lambda z square by c square. So if I compare all three values of 8xyz, it will be equals to, basically I'll get x square by a square equals to y square by b square equals to z square by c square. So from here what I'll get is, if I use the given relation, that is x square by a square plus y square by b square plus z square by c square equals to 1. So from here I'll get 3x square by a square equals to 1. That basically gives me x square equals to a square by 3. That means x will be equals to a by square root 3. I am neglecting negative value because length of a parallel loop pipe cannot be negative. So that's why I am taking only positive value. Similarly, I'll get my y as b by square root of 3, and I'll get my z as c by square root of 3. Now I need to calculate d square of f. That will be equals to basically differentiation of this. Let me just copy it first. So this is my df. So my d square of f will be basically equals to my d square of f will be equals to, again, differentiation of this whole term. So that will be equals to 8 of y dz plus 8 of z dy plus 2 lambda by a square dx times dx plus 8 of x dy plus 8 of z dx plus 2 lambda by b square dy times dy plus 8 of x dy plus 8 of y dx plus 2 lambda divided by c square dz times dz. Now, since if you remember the result that we got here, that is basically this result. If we use values of x, y and z here to evaluate lambda, so what we'll get is, so the result that we have is 8yz plus 2 lambda x by a square equals to 0, I guess. 8yz plus 2 lambda x by so from here I'll get 8 y is b by square root of 3, z is c by square root of 3 plus 2 lambda by a square, and x is a by square root of 3 equals to 0. So from here I'll get my lambda as minus 4abc divided by square root of 3. This is value of lambda. Now I need to check the sign of d square f by d, d square f, so that will be equals to, now my d square f was equals to summation 8y dz plus 8z dy plus 2 lambda by a square dx. Now if I evaluate it, it will be equals to summation 8b by square root of 3 dx dz plus 8c divided by square root of 3 dx dy plus, or it will be minus only, minus 8abc divided by a square root 3 dx square summation, this a balances this one, so it will be equals to summation 8b divided by square root of 3 dx dz plus 8c divided by square root of 3 dx dy minus 8bc divided by a square root of 3 dx square. So this can be written as summation 8b by square root of 3 dx dz plus summation 8c by square root of 3 dx dy minus 8abc divided by square root of 3 summation dx by a square. So this will be equals to 16 by square root of 3 summation c dx dy, because when you open summation, each of these terms will occur twice, minus 8abc divided by square root of 3 summation dx by a square, but we know that x square by a square plus y square by b square plus z square by c square is equals to 1. So from here we'll get 2x dx by a square plus 2y dy by b square plus 2z dz by c square equals to 0. So from here we'll get dx by a plus dy by b plus dz by c equals to 0. That will basically give dx by a plus dy by b. That will basically give us that. So this will basically give me summation dx by a square equals to minus 2 times summation dx dy divided by ab. So it will be equals to minus 2 divided by abc equals to summation c dx dy. So if we plug this value in d square f, that is here, so what we'll get is 16 by square root of 3 summation c dx dy minus 8ab c divided by square root of 3. So if I plug in this value here, so it will be minus 2abc summation c dx dy. So this simplifies to this abc balances this one, so it will be 16 by square root of 3 summation c dx dy plus 16 by square root of 3 summation c dx dy. Now from here let's plug in the another value, because this won't guarantee us that this is greater than 0. So we'll plug in value of this term, that is c dx dy, in order to ensure that d square f is less than 0. So it will be 16 by square root of 3 times abc divided by minus 2 summation dx by a square minus 8abc divided by square root of 3 summation dx by a square. So this will be equal to minus 8abc divided by square root of 3 summation dx by a square minus 8abc divided by square root of 3 summation dx by a square, which will give me this as minus 16 abc divided by square root of 3 summation dx by a square, which is basically equals to minus 16 abc divided by square root of 3 dx by a square plus dy by b square plus dz by c square, which is less than 0. So from here we got that d square f is less than 0 at x equals to a by square root of 3, y equals to b by square root of 3, and z equals to c by square root of 3. So from here we got that f attains basically the volume of parallelopiped is greatest at x equals to a by square root of 3, y equals to b by square root of 3, and z equals to c by square root of 3, and the volume is 8xyz, which is 8abc divided by 3 square root 3. That is what we were supposed to show. We are supposed to show that the volume of greatest parallelopipe that can be inscribed in the given ellipsoid is basically this. So we have shown this completes the question on real analysis asked in 2025 examination, and this also completes our real analysis module. We'll start with next subject in next video. Thank you for watching, and please do like, share and subscribe the channel.